we've only been doing this for how
It's been
many
about 10
episodes?
minutes. About
10
10 minutes of
minutes.
troubleshooting, something we should be good at after 2.5 years.
Oh, it's my first time. I'm just trying to figure it out.
That's what my wife says to me. Anytime I do a simple thing wrong in the house, like I open a bag and I do it too hard and I rip the whole thing open, she just looks at me. First time opening a bag. Yeah.
It's tough. They're
Sadly.
tricky. They're tricky. I mean, you have like the bags that you're meant to like pinch and open, or the double pinch, the like the pre-ground espresso bags that are vacuum sealed, and you somehow need to like apply your entire body weight of force just in your fingertips to open them. Dear Lord,
Yes.
how?
Yeah.
Ow! It's too
Ugh.
much. Oh Lordy. How have you been, Benjamin?
I've been good. I just had a regular, since we've last recorded, it's just been a regular, standard, boring, nothing exciting happening couple of weeks since we've last recorded. You know, go to sleep, wake up, eat. How about you,
The
Kavi? Anything
huge.
exciting happened to you in the last couple of weeks?
Oh, I see what you're doing. Um, I've been on a very fun and wild roller coaster of a ride, um, scientifically speaking. So, as I guess you're alluding to,
I am
I
alluding to it. You're right. Happy birthday, Kavi. It's been a wonderful another trip around the sun. Congrats and mazel and all the good stuff. Happy birthday. There. Hey.
thank you. I appreciate that. And that's the episode.
That's the episode. Kavi had a birthday.
the,
Ta-da.
the gang wishes Kovi a happy birthday. Do, 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 do. And that's the episode. Um, no, it's been crazy. I I imagine that what you're really alluding to is the paper I just published recently. Is that the plan? Is that what you're talking about?
I was going that way, yes. Kavi, what'd you do? How was work? How's work, Kavi?
So how was school? Well, well. So I for folks who don't know, like I find cool stuff in space and figure out what it is. Um, thank you for coming to my TED talk. Um, basically, my whole shtick for the past 3.5 years, maybe even slightly longer, is find things that go bang in the sky, specifically at radio wavelengths, so not like the nanometers sort of wavelengths of visible light that our eyes can see, but more like centimeters, meters wavelength that radio telescopes see. And basically finding things that go snap, crackle, and pop in the radio sky and figuring out what they are. And sometimes that's a relatively quick process, and sometimes it takes 3 years.
We are, of course, talking about Kavi's recent. I don't know if I don't know how to phrase this rightly, but your discovery of the long period radio transient ASKAP J1745.
Yes.
First
That
things first. First things first.
sure.
One, why is it called ASCAP J1745? Two, ASCAP J1745 is a bit of a mouthful. You've been discussing this for, I'm sure, a very long time as you're doing your research and making your paper. Did you come up with a shorthand nickname for ASCAP J1745, or do you say it by its full name every time?
Well, like a parent only says their child's full name when they're really upset with them. I've been, I guess, upset with this source for quite a while. No, we tried to come up with a nickname. It didn't quite stick. Speaking of upset parents, my mother was quite upset on my behalf. She said, "You know what? Why didn't they name the source after you? Like you found it, you should get to name
Yeah.
it." And fair. I understand that comes from a good place, but astronomers, generally speaking, will name things according to what telescope or project was used to find it as kind of the prefix. And then the main chunk of the name is basically telling you the phone number, or like the cosmic phone number or location, the coordinates in the sky. So the like right ascension and declination, which is basically telling you like how far this way and how far that way in celestial coordinates, is the source. So it's got a right ascension of 1745, and then it has a declination of minus 50, 51. And there are, additional points after the decimal there and additional units, but that's the closest shorthand that we have. And what else? Oh, ASKAP.
ASKAP.
Yes.
That's the telescope, yes?
Yeah, exactly. Yeah. So ASKAP is the Australian SK Pathfinder telescope. So ASKAP is located here in Australia, in Western Australia, at Yarimana Ilgari Bundara, which is the traditional name to show respect for the traditional landowners and native title holders in that community in Western Australia. It's owned and operated by CSIRO, Australia's national science agency, and it's kind of had this really important role over the past few years to be, as the name suggests, a pathfinder for the SKA, which is this massive multinational effort to build the biggest and best radio telescope in history across multiple continents.
Was there part of it here in the U.S.?
0% of it is in the US, actually.
Okay.
The US does have some cool radio telescopes coming online. So the VLA, the Very Large Array in New Mexico, is going to be getting an upgrade soon to be called the next gen or the NG VLA. There's also the Deep Synoptic Array in Owens Valley. Not your Owen, a different Owen.
Okay.
And just let them know. So the DSA is basically a massive array of, I think it was, when I visited Owens Valley, it was the DSA 110, because it's 110 dishes. They then planned for the DSA 2000. It's going to be 2,000 telescopes. I think they've kind of de-scoped and re-scoped that project. But yeah, there's some impressive stuff happening in the US, but not the SKA. The SKA is basically lower frequency stuff is happening in Australia. That's kind of like tens to hundreds of megahertz frequencies. So call that like meters wavelength. And then the gigahertz frequencies telescope is going to be basically, if you've heard of the Meerkat radio telescope in South Africa, so the gigahertz frequencies SKA, called SKA mid as opposed to SKA low, is going to be an extension of Meerkat. And basically, with their powers combined, these two telescopes are going to explore the universe from tens of megahertz to tens of gigahertz, and basically give us completely unprecedented resolution and views of the radio sky.
Okay. Jeez Louise.
It's
so
a lot,
many pieces. So many pieces growing. Massive. I mean, the pieces we have now are massive, and they're making more.
Yeah. It's
so,
pretty cool field.
ASKAP J1745 is a long period radio transient. Next question. What exactly is a long period radio transient?
What is that? Yes.
This thing you discovered. What is it?
What is it? I don't know. It just goes bang. So long period radio transient. So maybe let's break down each part of that.
Break it down, Kovi.
Break it down. So transient. I'll start from the end because I read backwards. Like Hebrew or Arabic. So transient is basically a thing that goes bang in space. So people will often use transients, astronomical transients, and astronomical variables interchangeably. Basically, if something wasn't there when you look through a telescope and suddenly it's there, or it was there and it was really faint and suddenly it's like gotten super bright. That's a transient. The radio part is, well, we're looking at radio wavelengths or radio frequencies, and then long period. So when things are variables, because right, sometimes they just go bang, they appear, they're there, and then they disappear, like a supernova, let's say. There's nothing there. It's just a one star in a distant galaxy. Suddenly, the star is brighter than the whole galaxy. It flares up and it fades over weeks or months. The periodic part is where things get interesting. So, as I think we've spoken about in the past on the show, there are these things called pulsars, which are basically after a massive star goes supernova, the kind of remnant, what's left over, is this dense core called a neutron star. And basically from angular momentum, you have a star that's this big, holding out my hands quite wide for those listening. When that explodes, you have an amount of material or mass that then shrinks down and to this big. Now I'm holding my hands closer together. And just like an ice skater holding their hands out or bringing their hands in, they'll start to rotate faster. So that's conservation of angular momentum in one sentence or less. So neutron stars rotate really, really rapidly. And when you have neutron stars that produce radio light, they're called pulsars because they flash, they pulse or pulsate, kind of like a lighthouse every time they rotate around. And these things do like millisecond to second periods. Like every time they spin about on their axis, that's one rotation, that's one period, and that's the rate at which we see the pulses.
In a millisecond?
Yeah, milliseconds.
Good
to seconds.
Lord, that's fast.
I know. Blink and you miss it. So when long period transients, or LPTs for the cool kids, were first discovered, they looked like pulsars. They quacked like pulsars. They were found in radio. They were really bright, like intrinsically bright. If we were guessing or trying to estimate their distance, the light was very polarized, meaning that it was, as the light wave moved through space, the polarization is just like the axis in which, or the plane in which it's oscillating, or if it's corkscrewing, it's circular polarization. So it was very much like pulsar-like, except for the fact that it was pulsating too slowly. And this is when things got weird, because the physics as we understand it says, well, if the radio pulses from a pulsar are made by its rotation and magnetic field and yada, 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 if it rotates too slowly, that physics, that model breaks down. And the like kind of standard way that we explain radio light from pulsars doesn't work if they're rotating too slowly. So hence the name long period, because they were much longer than pulsars, and things continued to get wacky over the past few years as we discovered more and more of them, with periods of not just tens of seconds, but suddenly tens of minutes and even a few hours. So that is kind of the background to LPTs, to long period radio transients, and why they were such a mystery.
In reading the article, that was on Nature and a couple other places that also posted the news about it. One quote I keep seeing on all of them was, unlike 10 of the 12 known long period transients. Yours, ASKAP J1745, beautiful name. I'd be proud of that name. What is ASKAP J1745? Its origins are now confirmed. What does that mean by origins? Where it came from, or the series of the coincidences that led to it becoming what it is?
I see. Yeah, this is a good question. So since the first discovery, and like there were things that kind of looked like LPTs called galactic center radio transients that were discovered in 2005. Not clear if these again, too many acronyms. Astronomers love acronyms. Not necessarily clear if GCRTs and LPTs are the same or overlap. But let's ignore GCRTs for a second and say that there's about a dozen or now 13, including this source, known LPTs. And when I say known, I mean we've found them at radio wavelengths and they're doing all the things that make us think they're an LPT, right?
Right.
But there are 3 of them that we have no idea what their distance is. The rest of them we're pretty sure are coming from within our galaxy, so relatively nearby in astronomical terms. They're not coming from another galaxy like a fast radio burst or something like that. But what's weird and so you can talk about like knowing roughly what, like we know what direction they're coming from, we know roughly how far away most of them are. But the real question about the origin is, what is the physical system in space that's making these radio bursts, right? Is it a pulsar that's rotating really slowly? Is it some sort of weird star? We did not know. That was the real mystery. And so there have been, prior to this paper, there have been 2 cases where an LPT was found. It looked like an LPT, quacked like an LPT, but optical, a follow-up with like optical, like visible light telescopes showed us that even though it was quacking like an LPT, it was there was something star-like in the system. So those 2 previous examples there, when you look at like the chemical fingerprint, like the spectrum of optical light coming from it, it looked like an M dwarf star. And then when you looked at, just like in Star Trek, right?
That's where I am.
And so for the first time with these 2 other papers, it was like, oh, okay, so maybe not all LPTs are weird pulsars. Maybe some of them are have some relation to stars. There've been some suggestions that you could have a white dwarf star. So a white dwarf, for folks who aren't familiar, is in the same way that when a massive star gets to the end of its life and it collapses in a supernova, it can form a neutron star. A less massive star, so let's say like around the mass of our sun, when it depletes all of its material for nuclear fusion, it will kind of fizzle and shrink down into a white dwarf. So it's the name white dwarf comes from it being white hot. It's basically just like a hot, sizzling lump of carbon that will continue sizzling and radiating out of all its heat for billions of years until there's no heat left. Like it's not actively a star on the inside anymore. So that was a hypothesis, like maybe it's a white dwarf just by itself spinning like a neutron star. Problem is, we never saw a neutron star, we never saw a white dwarf by itself giving off radio light. So we thought, okay, if there's a white dwarf in the system, it kind of might need to be a white dwarf in a binary, like with a companion star, and interacting with it would be the way that's producing radio. And so the 2 previous examples showed chemical fingerprint looks like an M dwarf. Based on the timing, based on the light, it looks like these systems could be binaries. And there's some like extra light that we're seeing when we look towards the shorter wavelengths, the bluer wavelengths, towards like ultraviolet light, that suggests that there's a really hot blue star in this binary. And if it was normal hot blue star, it would be massive and we'd be able to see it. But because they weren't able to, they suggested that it's a binary of this M dwarf that they could see and a white dwarf star. So with our paper, for the first time, we've actually confirmed that it's a white dwarf and an M dwarf, and they're interacting in a really funky way.
Oh, cool. Is the reason that you were able, I mean, we only know of about a dozen of these things.
Mm-hmm.
But now with what you found, are you able to find more of them easily in theory, or still tricky to find them? Did you and kind of a follow up in
Mhm.
finding this thing? It was kind of an kind of a lucky bit of happenstance that you kind of came across it, and you were able to ascertain that the only reason this is happening because it's possibly a binary star, and thus you wrote your fancy pants paper.
Yeah, I mean, it was. I think the scientific word is serendipitous, but yeah,
There you
it's like
go.
sheer dumb luck. Honestly, like
Thank you.
we in these surveys that we're doing using pathfinders or precursors like ASKAP and Meerkat, in the lead up to the SKA, we're basically surveying huge chunks of the sky, and we're doing that repeatedly. And honestly, that's the only way that you can find weird things like this. You have to just like be casting a massive net
Scan it
and
all.
just get all of it, all the data, and then it becomes a problem because you're like, well, crap, how do I actually deal with this massive amount of data? Like ASCAP produces, I think, 12 and a half terabytes of raw data every second.
Ugh.
Um, like you could, yeah, it's bonkers. So we were using a new method to filter out any light that wasn't circularly polarized, light that wasn't corkscrewing or spiraling as it moves through space towards us. And so we go from like the 3 million points of radio light in the all sky catalog to about 100 things once we use that filter. Um, and then most of them are basically stars or pulsars, except for this one guy that was an LPT. Um, I think we'll need to. So yeah, to answer your question, to answer the first part of your question, we'll need to keep doing that to find weird objects like LPTs. But I think what's cool about this discovery in particular is that now that we've identified the origin, like you said, we figured out what system is, at least for a subset of the LPTs, definitely producing this phenomena. We know about lots of stars like that. And so what astronomers can turn around and do is say, cool, so you found a white dwarf in a binary with an M dwarf, and that's producing LPTs. So yes, we can keep looking for LPTs separately with your big fancy pants surveys, but why not now just target these white dwarf, M dwarf binary systems, watch them for an entire orbital cycle or for multiple orbital cycles, and then with that, hopefully see, are we seeing similar behavior at radio, X-ray, yada yada yada.
When you set the filter to reduce the selection of things that you scanned to a manageable sum of stars as opposed to
Yeah.
the megaterabytes worth, is the reason that you're able to figure out that this was something special because it was oriented at a certain way, like edge on, or at the or you see it from the pole, or is it because there was something in the background that made it more visible, or maybe the fact that there's nothing between you, the viewer, and it in space? It was a clear enough line of sight.
It's an interesting question. I think that the orientation of the system came later from studying the optical. Um, the reason that it was worthy of follow up was, like I said, like the rest of the 100 things that we found, we basically were able to cross match to existing optical catalogs and or existing pulsar catalogs. Be like, cool, these are stars, these are pulsars. It's exciting that most of the stars hadn't been detected at radio frequencies before, but star is star, pulsar is pulsar. This guy had no clear match, so that's why it was interesting to follow up.
Got it.
Now, I think the other part that's interesting to your question is, was there anything in between us and the source? People have tried to figure out what the other LPTs are, and the reason why, except for those two that I mentioned before, the reason why that it's been kind of tricky is most of them have been discovered close to the kind of main disk of our Milky Way. The hence why I said that there was maybe some links to be drawn with the population of GCRTs, of galactic center radio transients. But the problem is that when you look towards the center of our Milky Way, if you get a chance on a clear night sky, if you're away from the big cities, you'll notice that there's, as the name suggests, a milky white fuzz around the center of the galaxy, and that basically means it's very dusty. It's very optically thick, meaning that it's kind of hard, or at least harder, to observe there at optical wavelengths.
That's why it was hard for the Enterprise to get to the center of the galaxy in Star Trek V. Okay, because there's that big massive stuff in the way. Cool. I went to the dentist yesterday and I got my teeth x-rayed. A typical bite wing x-ray delivers about 0.005 millisieverts of radiation, but a full mouth series of images, which is what I got, is about 0.1 millisieverts. So I got that much radiation yesterday, 0.1 millisieverts. How much radiation in units of dental x-rays does ASKAP J1745 deliver? Because it's pumping out a lot of radio waves and x-rays. So how much x-ray power are we talking about here? How many dental x-rays are we talking?
So this is not a calculation that was included in my paper. Surprisingly,
Or our friends who like to measure things in giraffes. I want to know how many dental x-rays worth of radiation this thing's pumping out every minute.
Okay, so from my very quick and probably inaccurate Google, a millisievert, well, like almost certainly inaccurate. So a millisievert is what is Google telling me? A millisievert is giving, when applied to 1 gram of living tissue, 1 millisievert corresponds to exactly 10 ergs of gamma radiation.
That's right.
Ergs are energy units. Now, putting aside the accuracy of Google's AI overview, so 1 millisievert, 10 ergs of energy. The energy that we were seeing at X-ray frequencies or X-ray wavelengths was something like 10 to the power of 30 ergs per second. So if 10 to the 6 is a million, and 10 to the 9 is a billion, and 10 to the 12 is a trillion. I don't know the words for what 10 to the 30 is, but
so a lot.
But basically, it's more than, it would be something like a million trillion times what you get from a dental X-ray every second.
Wow. There you go. That's all I wanted. It's a fair question.
I should have included that. I should have included the dental reference.
That in your paper.
I mean, what I can tell you, if we're talking about medical imaging, the magnetic field of the white dwarf in this sort of system is bananas, because so instead of millisieverts, we use Gauss units of Gauss to measure magnetic fields. So a fridge magnet has a magnetic field of a few Gauss, maybe a few tens of Gauss. An MRI machine, to connect back to medical imaging, an MRI machine has a magnetic field of maybe 1,000 Gauss. The white dwarf in this system has a magnetic field of 1,000,000 Gauss.
Wow.
And the M dwarf as well has a field of a few thousand Gauss, so a few times the MRI machine, and then the white dwarf is 1,000 times that. So, yeah.
Well, this kind of leads into my next question.
Oh yeah.
I assume the environment around a binary star system such as this is got to be pretty rough and extreme. But still, is it possible for there to be planets in orbit around them? Habitable or not, I don't know yet. I
Ooh.
mean, I don't care. I mean, but is it possible for planets to orbit such chaos?
Ooh.
Or is it's just too much? The entire system is pretty much devoted to these things annihilating each other.
I Well, so this is the interesting part. Some of the press articles about my paper have been calling it a vampire star and used language like cannibalizing and devour and demolish. And sure, like the white dwarf is ripping material from the M dwarf and gobbling it up. Um, but what's interesting about these white dwarf M dwarf binaries is basically if you start with a white dwarf and a star, like a low mass star, they're orbiting each other and they'll be orbiting with a period of, let's say days or tens of hours. And as they get closer and closer, the orbital period gets lower. And if they get close enough for the white dwarf's gravity to pull material from the low mass star, basically what happens is that the orbit will get closer and closer as it pulls more and more material. And then at a certain point, what can happen is that the low mass star becomes so stripped of material and mass that it's effectively a brown dwarf. And there's a really interesting phenomenon called period bouncing, where basically it can go from long period, short, 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 short. And then once it gets to this stage where it's stripped all the material from the star, the system kind of starts drifting apart again. And you'll have this kind of white dwarf and a brown dwarf slowly drifting away from each other. So it's not necessarily destructive to the other star, and it's not necessarily, going to end with a supernova or anything like that. So you could have a planet in there. You could have a planet maybe orbiting the system further away. I wouldn't say it's impossible.
Okay. Knowing that we have about a dozen of them that we know of, and after just what we discovered with Mr. 1745, or Ms. I don't judge. How many more of these types of things do you think there might be in our local group, or in the galaxy as a whole, or in the entire universe?
Oh,
How common are they? Super uncommon, or relatively everywhere, or whatever? Like
I
in
feel
Fortnite.
like I feel like they should be. I don't. The short answer is I don't know. Um, the medium length answer is I don't know, but maybe there are people who have a better idea. And the longer answer is that there are lots of white dwarf binaries, right? It's a, there are, majority of systems out there are binaries. And as they evolve over time, you will have a lot of these systems where one star has evolved into being a white dwarf, and if it has a low mass companion, that companion can, eventually produce one of these. They're called accreting systems, right? Accreting meaning just pulling material from the low mass
Mm-hmm.
star onto the higher mass white dwarf. So you should have lots of those, but you could also, if the companion star is too large, you can end up with what's called a Type 1a supernova. That's basically when a white dwarf pulls too much material onto it from its companion star, and if the white dwarf reaches a threshold that's about just less than 1.5 times the mass of our sun, it'll be too much for the white dwarf to handle, and it will explode in a supernova. That's a Type 1a supernova. So you have multiple evolutionary paths that some could end up like 1a supernovae, some could end up like this system. It really just depends on how much stuff was in the system when it formed, how much of that stuff went into forming the two planets, and what their different kind of histories were.
Okay. What kind of, for discovering a space Rosetta Stone type thing as this is? What kind of celebrity status does that get you? Is it like I could walk into a restaurant and ask how long the wait is, and they'll look at you and say, "You discovered ASCAP J1745. Table's coming right up."
I don't think that would even happen in the lunchroom at my own university.
I thought you were gonna make some kind of a joke. Oh, sure, I go to my local whatever, and they know me, but no.
No, I mean, like you know how
Sorry.
you know how. Sorry, I let you breathe.
Go on.
In the same way that like some folks have like a birthday blues thing where you know you get all this attention heaped on you and then it's like, oh, I don't really know what to do with this attention, it feels weird, and then the next day it's like, cool, back to work, like nothing had happened. I think it's very much the same sort of thing when you in the scientific world when you make a discovery like this. Um, like, sure, there are some cases, not this case, but there are some cases that like totally change the game and change humanity, and there's a Nobel Prize waiting later. Like, A, that's not the case here. I'm not arrogant enough to think that it is. And B, even in cases where it is like that, it normally takes several years for you know the Nobel committees, etc., to make those sorts of decisions. But for the most part, when big discoveries are made in a field of research, it's generally like the birthday thing, where you know your research team will be congratulating you, your colleagues who work on similar things will be congratulating you. Maybe there's a bit of media, a few articles that go out, if there's a way to make people care about the science, and then you know the birthday's over, the press is over, and then it's just kind of you're working towards the next scientific paper or the next birthday.
That was going to be my next question. Now that we have the ASCAP J1745, yep. Are you going to study it for a while? Are you going to look for more of these for a while? Or now we're done and we're on to trying to figure out what the next odd, wacky radio something is in space?
Yeah, both.
Both.
So we already actually put out a follow up paper. So we were working with a team in Spain that was helping us. So it was a team in Spain that was connected to a team in China that was using the Chinese Einstein probe satellite, or telescope, but space-based telescope. And so this team helped us get the X-ray data for our paper. At the same time, they were like, "Oh, well, this would be really cool. We could get some more time on different X-ray telescopes and kind of do a bit of a deeper dive." And Nature astronomy papers have page limits and word limits, and there's kind of only so much that you can include. So we were already kind of triaging what X-ray data and what findings were necessary for like the main discovery classification, and what would go into a follow-up paper. So that paper has already been accepted by ANA letters, so Astronomy and Astrophysics in their letters journal. So that follow-up X-ray paper is already out. There's more work that we're doing to better understand the radio properties, and also things that we want to do to better understand the system on the whole. But me personally, I'm also kind of focused on some other different projects, like totally different stuff that are side hustle projects I've been working on that I'm passionate about. Some stuff with a really interesting supernova, some stuff with distant galaxies. But for a lot of the jobs that I've been applying for recently, I've been focusing on how we can use these same sort of approaches and techniques that we've developed to understand, not just to to find more of these weird LPTs, these weird long period transients, but to also understand how do they form magnetic fields, both in the white dwarfs and in the brown dwarfs, and then also brown dwarfs individually. So it's kind of like tree branches branching out into different directions. So there are like some things that are related directly, some things tangentially related, and then there's like a sapling being my unrelated supernova projects that have just developed on the side.
Keep mentioning that it was you, but there was a team. How big was the team? And are there any shout outs you want to give to anybody who did something extraordinary, like when you needed a pencil sharpened, they sharpened that pencil real sharp?
I mean, I wish
I'm sure there's too many to mention.
I asked all of them for a new pencil or a pencil sharpener, and they were all terrible. Nobody gave me a pencil sharpener. So I had to use crayons to write the paper.
Nice.
Which the folks at Nature were very perturbed by. No, just kidding. There was a pretty big team behind this discovery. So it was myself and 28 co-authors, and that it's actually there are some people in science who are very protective of their author lists. I think because of a perceived notion that when you're applying for jobs, they want to see that you're the one who did everything, or because they have this idea in their minds of, I'm the lone scientist and I have to do everything by myself unless I absolutely need to. I don't agree with either of those two things. I think that science is a team sport. I think that I could only make these discoveries because other discoveries were made. So like the previous LPTs that were discovered by people like Natasha Hurley Walker or Manisha Caleb. Manisha, who is actually, both of whom are collaborators and colleagues of mine. Manisha, who's actually helped me a lot with this paper. But yeah, because that's just generally the way that science works, I treat papers that way as well. And I think that I can never remember the way that the expression goes, but basically the sum efforts of all of these people is greater than, well, the whole is greater than the sum of the individual parts. I do have to say that all of the authors contributed in such an impressive and helpful way, ranging from radio stuff to optical to X-ray, ranging from theory to observation and simulation. I do have to, obviously my supervision team and my mentors directly have been incredible. I do, if I have to pick one person to give a shout out to, it would be Joshua Preston Pritchard. So Josh was a former PhD student in my research group, now working for CSIRO as a postdoctoral researcher. And Josh has been absolutely critical. He definitely won't be listening to this, so I could smack talk him all I want, but honestly, he's been such an amazing help and a critical component of a lot of the work I've done, but especially this paper.
When your paper came out, I quickly threw together a whole bunch of memes and I sent them to you. Which one was your favorite? Was it the Dr. Seuss 1 cap, 2 cap, blue cap, ass cap? Was it the picture of Mr. Bean with finger guns saying "Don't make me bust ass cap in your ass"? Was it the Great ASKAP with Steve McQueen jumping a motorcycle? Or was it the Star Wars droid ASKAP J1745 radio burst droid from Empire Strikes Back?
The Star Wars droid was definitely up there. Mr. Bean definitely made me chuckle. I feel like your favorite was the baseball player coming out to the plate.
With, the baseball player one was because I love baseball.
I think the first one, the 1 cap, 2 cap, blue cap, ASKAP, was my favorite, only because I'm constantly making jokes about all the different types of dwarf stars that I study, like 1 dwarf, 2 dwarf, white dwarf, blue dwarf, except there's no such thing as a blue dwarf, so it's white dwarf, red dwarf, or white dwarf, brown dwarf. So definitely was close to my heart. Yay. I like them all.
I'll be sure to share them with with everybody. Would you like to do, as we're getting towards the end of our time, would you like to do a random sneak attack of as of yet not yet used questions and quibbles?
Sure. Yeah. Hit me.
Let's test them out. Okay. All right. Sandwich protocol. Do you bite from the corner or do you bite from the edge?
Do I bite from the corner or do I bite from the edge? As the first bite? It depends what sort of bread it is. I feel like if it's like a thicker focaccia bread, my first bite would be from the corner. I don't know if that's always the case, though.
I think a corner just makes sense. If it's a wide piece of bread and you take it from the edge, you're basically smearing it on your cheeks both cheeks at the same time.
I think you're right. Yeah, I think gun to my head. If you're threatening to put an ASKAP in my ass, it would, yeah.
Okay.
That'd be the corner.
How far down do you let your battery go before you charge your phone? Have you ever seen 1% or you get to 40 and panic?
I don't panic. I actually kind of like if my phone starts getting below 40% and it's, middle of the day or I'm not, about to head home or about to head somewhere where there's a charger, I think I'll just switch it into battery saving mode and just accept my fate. And I've definitely got it down all the way, like even, to 0. So.
Okay. You're faced with a box of donuts. Is it taboo to take just half a donut?
No, I actually think that the best way to eat a 12-pack of donuts when you have different flavors is to cut them in halves or quarters and share them with the people you love.
Okay.
Wait, hold on. I need to get your answers on these last two.
Okay. I think taking half a donut is kind of weird. And only for this one reason. You see a box of donuts and there's a knife in there, and somebody had politely used a knife to cut a donut in half, or maybe a couple other donuts in half, whatever.
Sure.
I have 2 issues, and I've thought this through. One, they did not clean the knife between cutting one donut and the next. So there's a possible cross-contamination of flavors, right? They probably went through a jelly, and then they sliced a chocolate or an old-fashioned. You're mixing flavors. Number 2, there's the thought, how many hands have been touching how many donuts in this donut slicing operation? So I can't do that.
When it's a communal thing.
It's a communal thing if I just take one. If I bring in a box of donuts and there's enough for everybody, it's a communal thing. We're all having donuts now. I don't have to have your donut and his donut and their donut.
Oh, no, I mean, it's like if it's a communal thing at a workplace or somewhere where like you don't know what other people have done or how many hands have touched it. I see where you're coming from. I think that for me, this is normally like when we're going to a friend's place for dinner and there are going to be a bunch of people there and we're too lazy to make a dessert and we know that they like donuts, so we'll bring a box of donuts. When dessert time comes, one of us, one person, one knife, one set of hands, will cut the donuts into halves or quarters. So it's just one set of hands. But you are right that, the cross-contamination of the knife, more could be done to protect the flavor integrity.
That's right.
And battery-wise?
Oh, battery-wise, I let it go down. I don't charge it until it gets down into the teens. Yeah. I've read a few things in which it's better for the battery life of your phone if you let it go all the way down instead of leaving it charged. Because you're actually using all the parts of it, and there's a kind of atrophy that happens to your battery if you don't use the entire thing.
There is something to this. there is something to this that I've read, and I can't remember the exact science of it, but basically a lithium ion battery only has a set number of full cycles in it. And I think there's a similar, like, it's related to the reason why phones and computers now will not let you get to 100%. They'll kind of hover below that level. Or actually, if you are on 100%, so I know that with some laptops, for example, um, it'll switch from a mode where it's actively charging the battery to avoid overcharging it to a mode where it's just using the power cable as a power source, which is
Mm-hmm.
more healthy. Yeah.
What is one scientific discovery you hope happens in your lifetime, just so you can see it?
I feel like we need like smoking gun evidence of um, microbial life outside of Earth. Like there's probably half a dozen ways that we could find it just within our solar system.
Yep.
Whether you're talking about like fossilized bacteria or bacteria in ice on Mars, or extremophiles being detected in the geysers coming off the moons of Jupiter, like Enceladus, right?
Mm-hmm.
Or Enceladus, if you prefer to pronounce it that way. Um, so there's a handful of like high potential candidates just within our solar system. I feel like either that or something in the atmosphere of an exoplanet. Not asking for a techno signature or signs of intelligent life, but I really do hope that we get the bacterial microbial
Just
thing.
something.
Just something.
Absolutely.
Yeah.
I agree.
What
That's
about
my
you?
answer. Same
That's your
answer.
too.
Life.
What
Any
he
life
said.
outside. I think it would be a great unifying event on a lot of levels if we found out that there's something else out there. As corny as it is in the movies, when in the sci-fi movies when the aliens attack, uh, it that's a world unifying type of event. I don't want that to happen. I don't want aliens to attack us, but I do believe that we find something else out there, any level of life, um, that's going to put the brakes on a lot of things and or realign our efforts in a more positive way. I think just to study and learn about something alive elsewhere. I think I think it would be an incredible thing.
For sure. Nice.
All right, let's see.
One more.
Okay.
I like these.
What is one scientific experiment from history that you wish you could redo again today with modern tools and knowledge?
Part of me is going for the manhole cover nuclear test, just to like measure the. I just really want
Operation
to
Plumb
know.
Bob.
Plumb Bob. I just, if we have to test nuclear things, like in a hole in the ground is much better than in bloody Tahiti or in space, that would, end up with like us suffering from the radiation consequences. But like, desert in a hole, it's much safer. If you have to test it, do it that way. But then like, just to know, like, did we launch something into space? Like, repeat the experiment and try to measure it properly this time with like high speed. I feel like Mythbusters has probably done this. Like, surely they've tried.
I don't
Maybe not
know
with
if
the
they
nuclear,
could have.
but
That's a good answer. Did it actually go to space?
it feels like a wasteful answer, but I feel like it just for the boyish fun of blowing stuff up, I feel like I want to blow it up properly and measure
And
it.
to use Mythbusters as a verb, we need to Mythbuster up that entire experiment a few times
Yeah.
so we can make a bigger and more resilient manhole cover every single time so
Yep.
it can survive the launch. Because the two prevailing theories are that if anything made it to space, there wasn't much left of it, or it was going so fast, so hot, and the friction was so intense that it literally, this, like, what was it, 2 tons or something of
Something like
steel
that.
and concrete, it evaporated before you even made it out of our atmosphere. So I would like to add on to yours that need to Mythbuster it up and make something just so incredibly tough,
We need to have one of
and
those
put, of course, the mannequin on
ballistic,
top of it.
yeah, the ballistic gel mannequin, just not on top of it, because that would get destroyed immediately, but like a meter
Yeah.
away
Yeah.
or a yard away for those playing in America. 3 eagles away from the cover, just so that you could see like the shockwaves ripple through it. Oh, that'd be fun.
That'd be awesome.
Yeah, is that yours as well?
Yeah, I haven't really thought about it. I've had these questions just all queued up for when we have a third and fourth and fifth time repeating guests. We have to be prepared. I have a whole bunch more questions.
Gotta be prepared.
All right,
Nice.
cool.
This was a
Thanks
lot
for
of fun.
teaching us
Thank
about
you.
ASKAP J1745. The name
Thank
just
you for
rolls
listening.
off the tongue.
Honestly, we tried to come up with a good nickname for it, but everything felt too forced. So even a nickname didn't quite happen. But yeah, it was a really cool discovery, and I'm glad as a team that we made it, we put it out, high impact publication, and hopefully it makes some big contribution to at least this field of astronomy.
Absolutely excellent.
Yeah. Well,
good.
Great.
That was a good one. Where can people find you, Kovi?
Folks can find me at Fun Fact Science on all the social media platforms. Honestly, you could probably Google my name and find a bunch of stories about ASKAP J1745, or just Google ASKAP J1745. That's ASKAP J for
J17. Come on, dude. I didn't know anything about it. I know its name. Oh, yeah.
Check it out. There's some cool. Yeah, there's
just
an
give it its
article I wrote.
acronym. AJ. That's a good name.
AJ.
What up, AJ? Like
AJ.
from The Sopranos. The Tony Soprano's kid was AJ. That was great.
Anthony Jr. Yeah. Kid loved his gabagool. Yeah, where can people find you?
You can find me wherever you find science. Actually, Facebook's a big one. Go for your daily science facts and your daily collective nouns and links to all kinds of stuff that are sciencey, including links that Kavi writes and puts up because he discovers stuff. And if you want to see us making the sounds we're making, go watch us on the YouTubes or on the TikToks. And we have the short, YouTube shorts and the full length of the show. We're available wherever you get all your podcasts, which you've already found out by now. We also need to start doing this. If you like our show, please hit all the internet buttons for the liking and the subscribing, and leave us reviews and share with your friends. And this is our 93rd episode. No, 83rd episode, season 9, episode 3, but it's our 83rd episode. You got to catch them all, people. Like them all, and there you go.
Gotta catch them all. Great note to end on. Thank you, Benjamin. We'll see you all next time, the next episode of the Science Actually Presents The Nerd and the Scientist.
Bye.
Bye-bye.